Okay, hello Analysis 1A. In all three classes on Wednesday and Thursday, we pretty much hit the exact same point, which is we graphed this function. This was a very math-specific kind of problem, and okay, you will recall that we took the derivative and took the second derivative, made a sign chart for the derivative, made a sign chart for the second derivative, concluded that when the derivative was negative, the function was decreasing. When the derivative was positive, it was increasing. When the second derivative was positive, it was concave up. When the second derivative was negative, it was concave down. We then drew pictures of generic functions that satisfying these properties. It turned out that this function also factors nicely, so we made a sign chart for the function itself, and we put it all together to produce a graph. And the sort of very last thing we did in every class, sort of just at the end, was to talk about this thing called a point of inflection. What's a point of inflection? It's a point on a function or on a curve where the concavity changes. So either we change from concave up to concave down, or concave down to concave up. And actually, maybe some more interesting things to say about this, but first I'll just repeat the sort of last thing I said, which is, okay, in this function, notice the function is sort of decreasing, increasing, decreasing. So on the interval from -1 to 1, this function is increasing. What's happening at this point of inflection? Well, it's where the concavity changes from being concave up to concave down. But maybe phrased a little bit more helpfully or something without using so much vocab, it's the place where, and on a technical level, that means, according to my definition of concave up and concave down, that the tangent lines here lie below the curve and here the tangent lines lie above the curve. Well, but what I said in class was, okay, you should think of it as the place where, well, okay, this function's increasing, right? But here it's an increasing at a faster and faster rate from 0 to 1. Or sorry, from -1 to 0. And now it's the rate at which this function is increasing until x equals 0, at which point the rate at which the function is increasing is decreasing. So, okay. So this suggests a kind of broader and deeper sort of meaning of point of inflection. And okay, I think that's helpful to take now a real world kind of example. So this example was maybe very, very relevant in the lives of students, but now we're getting to the point where the financial crisis is something that happened before, well, when you guys were so little that you don't even remember it. But you've been alive for the whole thing. But okay, you know, this is very, very recent history, and I actually spent like a half an hour or something researching this on the internet, trying to find a really, really good picture. And for reasons which I'll explain in a minute, you kind of can't find a really good picture of what I'm trying to do here. What I'm trying to do is talk about the economy. So I put quotes around this because you know, think of the y-axis as just being like the economy. Now, obviously, I'm not an economist, and in fact, I've never even taken an econ class. So I barely know what I'm talking about. The economy is a complicated thing. It involves many factors and many people. You could measure it with by the stock market. You can measure it by the sort of gross national product output or whatever. But let's just take a kind of a person-centric view of the economy, which is that it's people who are employed. And so it's not ever quite this simple because the country is growing and people are entering and leaving the labor force. So usually people will talk about unemployment as a percentage of people who are employed. But here, let's just consider just raw jobs. And don't worry about the y-axis too much. Here's roughly what the economy was like. People had jobs. There were a lot of jobs. And I can tell you, because I remember this, somewhere in early 2008, the economy started getting bad. And by that I mean people started losing their jobs. And it was losing their jobs. And then in August of 2008, this is when the economy crashed. And by that, we mean that's when the stock market crashed. That's when all the mortgage crisis happened. And okay, well, then people started losing their jobs more. So notice that from this point, which is 01, 08, this is January 2008, I mean, to August 2008, the economy certainly lost jobs. But then, continuing through August, for the rest of the fall of 2008, not only did people lose jobs, but they lost jobs at a faster and faster rate. So the total number of jobs in America was decreasing, and it was decreasing at a rate which was increasing. And if you look at this, you can sort of see that here, not on this entire interval, from January 2008 to January 2009, it's certainly true that if we call this function f, that f prime is negative, which is to say that the number of jobs in America were going down. So a normal person would say that that's bad, right? When people are losing jobs, that's bad. And that's right. But not only is it bad, but also, if you look at this interval, we can talk about the second derivative. What's the second derivative? Well, the second derivative here is also negative, which is to say not only were we losing jobs, but the rate at which we were losing jobs was decreasing. Or that's a little bit, confusing to say it that way, but it's certainly true that the second derivative is negative. It's certainly true that this function is concave down. The rate at which we were losing jobs was increasing. But the rate, well, okay, I'll just leave it at that. All right, so then something kind of amazing happened right here in January 2009. And in January 2009, this is, okay, once again, multiple apologies because I don't really know what I'm talking about. But this is what people often, this is the moment that people often point to as the recovery. Okay, they use other terms for this. They say this, but this is basically when economists got really, really happy. And what happened in January 2009? Did the economy suddenly recover? Did people suddenly get all their jobs back? Was everything suddenly better? No, it's not true that in January 2009 things suddenly got better. In fact, they continued getting worse for a really, really long time. If you are a normal person, I consider myself kind of a normal person, then the worst time was right here. This is the relative minimum in the number of people in America with jobs. This was the bad place. After this point, things got better, legit better, as in like people really started gaining, the economy started gaining jobs again. But what did happen in January of 2009 was we had a point of inflection. And what is the point of inflection? This is the whole reason for this anecdote. The point of inflection is where in January 2009, where not when things started getting better, but when the rate at which they were getting worse stopped getting worse and started getting better. Okay, in other words, it's the place where the rate at which people were losing jobs stopped increasing and started decreasing. People continued losing jobs for an entire another 12 months. This is the entire first year of the Obama presidency, roughly speaking, was January 2009 to January 2010. For that entire first year of the Obama presidency, America, the economy, by any reasonable measure, got worse and worse and worse. More and more people lost jobs. But the point at which people the place at which people often pinpoint the recovery is this point of inflection. Okay, and it's because you sort of, if when things are bad and getting worse, before they can actually get better, they have to stop getting worse so quickly, okay? And so the point of inflection is the point where things stop getting worse. They start getting worse more slowly, is one way of putting it. Okay, yeah, and when you Google economic recovery, what you will find are many, many graphs which look a lot like this. And if you're a normal person trying to interpret these graphs are meant for like economists. you will be led to believe maybe that suddenly right here is where things started getting better. After all, didn't we change from red to blue or something like that? This person, I didn't make this graph, color-coded it this way. This is the point of inflection. It's not the place where things started getting better. It's the place where the rate at which they were getting worse started getting better. And you can get very easily confused until you look at what the actual y-axis is. Of course, this is time, but this y-axis is not what I showed you on the previous slide, which is jobs, so to speak. But instead, what you see here is job loss gains in thousands. So this is sort of like, this is not jobs. This is in some ways kind of like the derivative of jobs. This is the derivative of jobs. In other words, what this graph is displaying on the y-axis is how many jobs were lost per month. It's the rate of change of the jobs. And you will see that right here is the line y equals 0, which is to say that in November and December of 2007, just before things started getting bad, America gained jobs. So there were more people working in each of these 2 months. And then in January 2008, almost imperceptibly, there was a small loss in jobs. You know, we lost 10,000 jobs that month. Then in February, we lost more jobs. In March, more. In April, more. In May, more. My general memory of 2008 is that people didn't really think of us as being in a necessarily terrible economic state until sometime around August. And then what happened in August? In August, we lost 300,000 jobs. In September, we lost 450,000 jobs. In October, we lost 600,000 jobs. In November, we lost 800,000 jobs. And we continued losing more and more jobs per month. In other words, the derivative of the number of jobs we have kept getting bigger and bigger. Okay, and then this point where there's a point, this point, if you're looking at this graph casually, or if you don't know calculus and you're trying to understand econ, good luck. Because it appears superficially to the naked eye that there's a relative minimum here. But this relative minimum is the relative minimum not of like the economy. This is not when things started getting better, really. This is when things stopped getting worse so quickly. I'm kind of repeating myself now, but these blue bars that make the economists so happy, why are these bars all colored blue? Because now we're still losing jobs. We're still losing hundreds of thousands of jobs per month, but the rate at which we're losing those jobs is getting smaller. And so we're losing fewer and fewer jobs. And then finally here, around the end of 2009, beginning of 2010, is when we actually finally start gaining some jobs. Okay, and this is another sort of picture of the same thing. Notice that it's almost impossible to find a graph, I couldn't find one, showing this. And that's because economists usually don't care about people. They don't care when things are getting worse for people or getting better for people. They care about this point of inflection. And perhaps for good reason, because if you're trying to predict what the economy is going to do, you need to look for not just the first derivative, but for the second derivative. Okay, and yeah, this is another picture in which the y-axis is jobs lost per month. And you'll see that we lose more and more jobs, and here's where things are really, really bad. It's when the rate at which we were losing jobs was at its peak. Here we're still losing jobs until we get here is where the true recovery starts, in the sense that people start actually gaining some jobs back again. Okay, finally some math. Sorry, that was kind of inefficient. It's more fun if we do that live. So a math thing. What can I do with concavity? Besides, I think I've already convinced you that this is an extremely important concept, and in not just our simple position velocity acceleration graphs, but also in a more serious sort of analysis of changing functions. But okay, putting all that aside for a minute, let's just get to just a kind of a simple math problem. Here's a simple math problem. And let's just suppose for the moment that I want to find the extrema of this function. All right, let's do that, the relative extrema. Let's do that using the way we know how. So method number 1, take the derivative. All right, well, so I take the derivative of this function. What is it? Well, the derivative of this function is 5x to the 4th minus 5. Okay, and now, of course, I can factor this. So let me take out a 5. So that's x to the 4th minus 1. Okay, and this of course, can be factored as x squared minus 1, x squared plus 1. And so there's still a 5 here. So, okay, what is this derivative? This derivative is 5 x minus 1, x plus 1, x squared plus 1. And so, one way to find the relative extrema is just to stop there. This is something we already knew how to do earlier in the week. We're going to make a sign chart for the first derivative. What are the critical numbers? The critical numbers are 1 and negative 1. So I put negative 1 here, I put 1 here. This is a quartic, but of course, leaning on our pre-calc knowledge, this is always positive. And if x squared plus 1 is always positive, then it's, there's no sign changes happening there. Leading coefficient's positive, so therefore, this function will have a sign chart of plus minus plus. Okay, and what does that tell me? It tells me that my function is increasing, then decreasing, and then increasing. And so, based on the first derivative test, we have a relative max here. So we're going to have a relative max because the derivative changes from positive to negative because the function goes from increasing to decreasing, and we're going to have a relative min here. Okay, so if the directions for this problem were to find relative extrema, it seems that we've done that already. And if the prompt was to justify the existence of these relative extrema, then we also know how to do that. Let's practice that right now for a minute. The sort of magic sentence, as I called it on Monday, goes something like this: f prime changes sign from positive to negative at x equals negative 1. So, by the first derivative test, f has a relative max at x equals negative 1. You can shave a word or two off of this, perhaps, but basically every single thing I just wrote here needs to be mentioned. You need to explicitly reference a sign change in the first derivative. You need to reference the first derivative test, and you need to tell me where that sign change is happening, and then that the conclusion is that there's a relative max. Let's just do this one more time for the other one. F prime changes sign from negative to positive at x equals 1. So by the first derivative test, f has a relative min at x equals 1. Okay, this is what is required when you need to justify the existence of relative extrema. Okay, that was all old stuff. Now comes something new. Here comes the something new. I'm going to take the second derivative. Why should I do that? What does the second derivative have to do with relative extrema? Well, I'm going to explain in a minute. The second derivative of this function is very easy to compute because it's a polynomial. After all, the more you differentiate polynomials, the easier they get. So this represents 5 seconds of extra work or something like that. Looking back up here at this version, what we get is 20x cubed. Okay, so now let me make a sign chart for the second derivative. And all right, well, it's just a cubic with leading coefficient positive, so it's going to change sign at 0. And so this is going to be negative, and this is going to be positive. And my conclusion, therefore, is that my function is concave down, and here it's concave up. All right, what does that tell me, or why is that helpful? Well, watch this. Let's try to make a kind of a graph of this function, or like a little one. What happens when I plug in negative 1? let's see. When I plug in -1, I get 7, I think, right? Because 5 and 3 is 8 minus 1 is 7. So, okay, so up here at 7, and here's -1. All right. I already know, so this is what I'm about to do right now is instead of performing this analysis that I did over here. So what I want to do now is I want to say, well, what do I know about this number -1? I know it's a critical point, and specifically I know that the derivative is 0 there. And so let me draw in a little horizontal tangent because I know that the derivative is 0. Okay, and what about when x is 1? When I plug 1 into this function, what do I get? 1 and 3 is 4, minus 5 is -1. So when I plug in 1, I get -1, boom, boom, boom. And it's also true that the derivative at 1 is 0. So I also have a horizontal tangent here. Well, until I perform a sign analysis on the first derivative, I can't say for sure whether that I have a relative max or a relative min here, or perhaps neither. Okay, well, second derivative to the rescue, because what can I say about this point -1? Well, it's a number which is on this interval, right? And therefore, what I know for sure is that the function is concave down at -1. And if the function is concave down, here is where I'm finally, hopefully, convincing you that this big theorem that we proved in class today is useful. The big theorem that we proved in class today, which was quite hard, which is that when a function is concave up, that when the second derivative is positive, that the function will be concave up, where for me, concave up meant tangent lines lie below the curve. So in other words, the theorem is really just if f double prime is positive, then tangent lines lie below the curve. And of course, if f double prime is negative, then tangent lines lie above the curve. So here, our book needs this too, because they need the following argument. Here we are concave down. What does concave down mean? Down, down, down. It means the tangent lines lie above the curve. But look, this green tangent line is a tangent line. Let me draw it a little bit bigger and maybe label it or something. What is this line? It's the line y equals 7. It is one of the tangent lines of this function. It's the tangent line to this function at the point -1, 7. It's a horizontal tangent. Well, if the very definition of concave down means that tangent lines lie above the curve, then since this is one of my tangent lines, and since the function is concave down at -1, then I know that this tangent line must lie above the curve. And therefore, I can tell you that if this tangent line lies above this curve, then it means my curve lies below this tangent line. And if the curve lies below this tangent line, then in this tangent line has y value 7, it means that the curve is below 7. In other words, there's a relative max here. Okay, and repeating that logic now for the other critical point, x equals 1, it's certainly true that at x equals 1, the derivative is 0, so there is some kind of a horizontal tangent line. What is this line? It's the line y equals -1. But this point x equals 1 lies within this interval from 0 to infinity in which the function is concave up. So since concave up means tangent lines lie above the curve, concave up means tangent lines lie below the curve, then this green tangent line y equals 1 must lie below this curve. And therefore, my curve must look like this. And if this curve looks like this, then in fact, I have a relative minimum there. So I'm actually not writing this all down because I want to talk it out to you. But what I've just explained to you is this thing called the second derivative test. The second derivative test, which is the title of this slide, is another theorem about how to find relative extrema. It is an alternative to the first derivative test. So method number 1 for finding relative extrema and justifying relative extrema is doing all of this. Sorry about that weird thing, right? All of this, what did we do? We not only found where the first derivative was 0, but we made a sign chart for the first derivative. We analyzed the sign of the first derivative, and we applied the first derivative test, which says that when there's a sign change in the first derivative, you have a relative max or a relative min. Alternatively, if we didn't feel like doing everything in this big blue circle, we could do something else. And the something else is to use the second derivative test. The second derivative test skips over all this and instead just takes the second derivative. Then, plugging the critical numbers, or just looking at the critical numbers and determining whether the function is concave up or concave down there, we can see that since the horizontal tangent at that point must lie either above or below the curve, then we have a direct proof that the curve never gets bigger than that y value or never gets lower than that y value. In other words, we have, by the very definition of relative max and relative min, we have a relative max here and a relative min here. So, all right, instead of stating the theorem more generally, I'll just explain how you justify it for this example. Here's what you do. You say, okay, f, you're considering this x value, this critical number, -1. You say f prime of -1 is 0. In other words, it's a critical number. And f double prime of -1 is positive, which it is. No, sorry, it's negative. F double prime of -1 is negative, which means that the function is concave down. And if the function is concave down, then since it's concave down and since the definition of concave down is the tangent lines lie above the curve, then no point on this curve can be nearby, can be bigger than 7. So by the second derivative test, f has a relative max at x equals -1. And similarly, f, I'm not going to be able to fit this in here, but since f prime of 1 is 0, in other words, 1 is a critical point, and f double prime of 1 is positive, by the second derivative test, f has a relative min at x equals 1. Okay, and so maybe I'll circle this in like red or something. This is another way to find relative extrema. Instead of showing that there's a sign change in the derivative, you prove that it's a relative max kind of directly, so to speak. It must be a relative max. I know this function can never go above 7 because I know it never touches the line y equals 7. Why? Because the line y equals 7 lies above the curve. Why? Because tangent lines, as we proved, for a concave down function lie below the curve. And I know this function's concave down because I took the second derivative and I made a sign chart for the second derivative. So the second derivative test says you plug your critical numbers, you plug your places where the first derivative is 0 or undefined into the second derivative. Usually it's when the derivative is 0. You plug those into the second derivative, you see whether the function is concave up or concave down, and you thus conclude whether there's a relative max or a relative min there. The only time that you really ever use this doesn't come up that often. It comes up when, for whatever reason, it would be extremely difficult to make a sign chart for the first derivative. There are times when making a sign chart for the first derivative might be really, really difficult. And this is easier. By the way, you don't even need to make a sign chart for the second derivative per se. You could have just have plugged -1 into the formula for the second derivative and just gotten a number and noticed that it was negative. So you actually don't need to make any sign charts at all. And you could have just gotten the formula for the second derivative and plugged 1 in and noticed that what you get is positive. In fact, you just get, when you plug in 1, you get 20. When you plug in -1, you get -20. So you don't even need to make this sign chart at all. Okay, hopefully that was a clear explanation of the second derivative test, which really has nothing to do with points of inflection. That's a misunderstanding. It's just it's a second derivative themed alternative method of finding relative extrema. Okay, I think I've said that very, very clear. So hopefully you watched this video on 2 times speed. Goodbye, everybody.